All right, so let's talk about the example for black body radiation. Again, remember last time we were going through coming up with the relationships for radiation exchange between surfaces, and then for view factors. And so now we want to do is combine these ideas of how do we model radiation exchange when we can actually compute things like the fraction of light that's going from one surface to another, right? The view factor. So this example that we'll go through for the first few minutes here is this geometry that's shown. You have a tube inside another tube. There's like this annular space. And then there's two caps on the end of this thing. You have, let's see, draw here. You have this kind of surface that's capping one end. You have a surface that's capping the other end. And then we're looking at radiation exchange between inner surface, outer surface, the capped surfaces, and sort of all the possible paths that radiation can go. Let's assume now that the outside of this is, let's say, well insulated, so we're not, well, let's say not well insulated. Let's assume that the outer surface is held at a constant temperature, but we're only modeling radiation internally. Right? So we are concerning ourselves when it comes to like view factors with only looking at what's happening inside this space. Things to point out. So first I said we're holding the surface temperature constant. We're also holding the inner surface temperature constant. Surface 3 is at 100 K. Surface 2 is insulated. So we have an adiabatic and then 3 constant temperature surfaces. We can compute the area of each of the surfaces as shown there. Pretty straightforward, just area of cylinders. And then maybe the only one is like the end caps are the difference between the outer and inner radii in terms of the area. So what's the approach for this, right? We want to be able to model the radiation exchange. We need to know how much light that's being emitted from one surface hits another surface. So we have to start by computing the view factors. And we have to do that for all possible combinations of surfaces. So you have a 4x4 matrix of view factors that we have to fill out, 16 of them. All right, so we'll try not to be too tedious about it, but I'll show you maybe how you go about doing this, and you get a clear example. Yeah. So
where the surfaces make contact, are we just going to kind of ignore?
So this is saying that the surface 2 is actually only this bit. It's like from here out to here. It's kind of just this donut or flattened donut, right? Yeah.
Should that bottom equation say A4 instead of A3?
Yeah, I probably should. Let's see. Because we are giving A3, so this is A4. Thank you. So we know all the 4 areas are known to us. Okay, so let's go through and compute the view factors. The hard part is sometimes figuring out kind of where to start. So we could go by just saying, all right, let me just number these surfaces out so we know this is surface 1 in the middle. This is surface 2 over here. This is surface 3. And surface 4 is at the top. For some reason, we use P for surface 1 and what? P for surface 1 and S for surface 4. I don't know why that was done. Okay, so let's maybe start by seeing if there's anything that's like obvious about the problem. If we look at this, is there a view factor that just by inspection we know what it is? Exactly. So we'd say, to start, we know F11 is equal to 0. That surface can't see itself. So any light that's emitted is not going to hit that surface. Okay, so then I guess since we started with 1, let's continue looking at all the view factors that have to do with 1. So let's go F12. F12 is going to be the dowel, I guess, or the pin. What do you call it? Pin inside here, out to this outer surface. There's no obvious like inspection or other technique we could apply, so we actually have to go to a library for this. So we would go look in the Ease library. It turns out, I won't show you that, but it turns out that that can be obtained with this function f3d_6. So you would presumably give it like the diameter and height of that inner surface and then the diameter of this outer, the base surface, and that would give you the view factor. So, okay, we have F11, F12. What else can we know now that we have this information? could, yeah, we could do that. Let's, before we get there, just for sake of keeping it in my order, let's look at 3 to 1, right? 2 to 1 or 1 to 2 and 1 to 3. They're the same, right? It's the same geometry. So you could say by symmetry or by equivalence, it's also F1, 3. So let's see. Okay, we have F1, 1. We have F1, 2, 1, 3. And then we're left with F1, 4. So F1, 4, I guess we could probably try to go look at a library for that, but we actually don't need to. Right? We have enough information. We have all 3 of the other view factors. We just have 1 remaining. This is an enclosure. So we can use the enclosure rule here. And we would just say F1, 4 is equal to 1 minus F1, 2 minus F1, 3 minus F1, 1. So there may be multiple ways to evaluate a view factor, right? You don't just go with the easiest one, the one that completes the equation in the easiest way. So we have this. I guess we could. I'll flip back and just kind of show you how this goes as we're doing it. So if we look in ease, first of all, I've got the geometry entered here. I've got the areas, and then I've got the view factors. So the way that I would approach doing this, if you were doing it in ease, would be something like this, where you're using this matrix notation, and you're doing this because it then becomes easy to loop through them later, like using a duplicate statement. If you're doing this in Python, you'd have to like somehow program the relevant view factors in, so it might be good to start by doing this kind of stuff in ease. But anyway, so you have the areas, you have the view factors, and the indexing would go for first surface, second surface. So you can see I've just entered here what we had talked about. If I solve this and we look at the answer, we look in the arrays table, you can see that we've filled in that first row, so F1, 1, 2, 3, and 4. And it's good at this point to maybe stop and look at it and see if the magnitudes kind of make sense. So it's often that you'll maybe make a geometry mistake or divide by 2 error or something like that, and things will just not look right. But in this case, we're saying F from 1 to 4 should be a pretty big number, I guess. That makes sense. You have this pin, and most of what it's seeing is the surroundings. F1, 2, F1, 3, they should be equal to each other. F1, 1 is 0. So that all kind of lines up. So this is just how you'd start doing it. But you can see, as we go through, we're going to start filling out these spaces here and there, and you're going to get enough information to start filling everything in. It's like a Sudoku. So, okay, so that's the approach. Okay, that's 4 of the 16, so let's keep going. So let's look next at, okay, we have all this stuff related to F1 to another surface. Let's look at F4, 1. So let's look at surface 4, F4, 1. So how would we go about evaluating F4, 1, either given the information we have or what else is available? Reciprocity. So we have F1, 4, and we know the areas. So we can just say F4, 1 is equal to A1 over A4 times F1, 4. Okay, so we compute it that way. That's easy. Let's see, F4, let's see, what else could we do? We could do F4, 4. So F4, 4, that is the view of the outer shell to itself with some obstruction in the middle. Turns out there's a library for that, so you can use a library. That is F3D underscore 5. So we would get it that way. We do know that F4, 2 is equal to F4, 3. Right? F4, 2 and F4, 3 are the same. So with this, we actually have enough information, right? Even though we don't know what these are, we know they have to be the same. So through the enclosure rule, we know these two, subtract off, and then divide by 2. And we're sort of left with what those are. So F4, 2 would be, by enclosure, 1 minus F4, 1 minus F4, 4 divided by 2. Okay, so that's, now we've got half of them. We have surface 1, surface 4. Let's do maybe surface 2 next. So let's look at F2, 1. So first, I guess, F2, 1, what do we know? We already know F1, 2. So again, reciprocity. That would be A1 over A2 times F1, 2. F2, 4, we know F4, 2, so that's reciprocity. A4 over A2, F4, 2. F2, 2, that's the little donut shape to itself, is 0. And then F2, 3 is going to be enclosure rule. So equals 1 minus F2, 1 minus F2, 2 minus F2, 4. Okay, so that's 12 of the 16. But you can see we're kind of have enough information now where we can move more quickly getting through this. So for the third surface, F3, 1, well, we already know F2, 1. So F2, 1 by symmetry or equivalence has to equal F3, 1. Right? It's the same geometry, just flipped around. So F3, 1 is equal to F2, 1. So that's one where you'd say, you know, by inspection, I am making this judgment. F3, 4 equals F2, 4, again by inspection. F3, 3 equals 0. F3, 2 equals F2, 3. So it turned out that, you know, because that surface is exactly the same, it's just exactly the same both ways.